So, let's see here. Welcome to today's lecture on software product lines. This is one of the more successful examples of the application of architecture, and it has to do with the benefits you get from having an architecture when you share assets that are reusable. So we're going to talk about software product lines and the fact that we have the need for more advanced technologies when it comes to software development, because most of you are familiar to this situation when you have a one product at a time kind of approach. You develop your assignment system. You develop your hobby project, and so on and so forth. But if you look into the real world where you have a focus on deadlines, where you have a time and budget, and you have a software quality requirement, etc., the ballpark is different, and suddenly you have to focus on other things than the actual, well, just develop a single system. And one of the things that you have to focus on is software reuse, because it turns out that software reuse actually shortens the time to deliver. For obvious reasons. If we don't have to develop our operating system from scratch all the time, we save time. So this is what we do. We have installed an operating system on our computers, so kind of reusing that system every time. The same with our libraries. We don't develop a communication package every time. We reuse that. So that saves us a lot of time, but we also get more than time from it. We actually improve quality. And the quality improvement comes from the fact that since people are reusing the same software package in different contexts, in different applications, for different purposes, well, it gets more used. And the more we use a software package, the more tested it is, because this is actually testing in the wild. So over time, as more and more people are using this reusable or this packaged, reused package, well, we actually get it more tested, and it can improve in terms of quality. Okay, so how do you build something that is reusable? Well, this is actually the focus of today's lecture. How do you build something that is reusable? And it's also, how do you build with reusable elements? So there are two sides of things here. There is the development for reuse, and it's the development with reuse. And as you will see, the software product line is an approach that considers both development for reuse and the other side where you develop with reuse. But the 5 dimensions here, according to a well-known guy in software reuse called Kruger, he states that when you develop for reuse, it's very important that you have really good abstractions. And second is that you can take these abstractions and you put them into some kind of library where they are kind of organized and easy to find. So what is a good abstraction then? Well, that's actually quite tricky to figure out, because what could be a good abstraction for me could be the worst abstraction ever for you. Because in order to find out the best abstraction, we have to know something about the context in which it will be used. Because you remember from your OO, A, and D class that you create your abstractions depending upon the context. So how should we do then if we don't know the context? Well, you can try to be very general, of course. The problem with being general is that there will not be too much to reuse, because you try to cover like everything broad. Okay, but the other side of things is then, of course, that you go vertical and you try to be very specific. You try to come up with very specialized abstractions. And the problem there is, of course, that, well, you will not be able to be useful with your abstraction in too many contexts. Because when it comes to development with reuse, if you look at it from the other side, well, the first problem you face as a programmer is to find the reusable asset. Okay, find a reusable asset, sure. How do you do that? Well, today, lots of people, they use a search engine to do that. And then you find some, and then you study it and try to figure out, what do I need to do to make this reusable asset fit my problem? And then you integrate it. So if you can establish a system that supports abstraction and classification for reuse, and identification, specialization, and integration when you develop with reuse, you will be kind of successful. And as you will see today, the software product line is actually successful in this. And I will try to explain the reasons for that to you later. So, development with reuse. What is that? And what is the role of the software architecture? Well, what we can say is that the earlier you discover that you can reuse something, the better. The larger the chunk of reusable assets you can identify, the better. So someone once said that the best type of reuse is when you can take a package like Microsoft Word and it meets all the requirements. You have to do nothing. But the role of the architecture when you develop with reuse is actually that you specify, you remember, the responsibilities of your components and the interfaces of your components. Okay. Having that gives you a great opportunity to use them as search criteria. You're looking for something that satisfies these responsibilities and provides and requires these interfaces. So the architecture is actually the basis for your specifications that you use when you search for usable assets. Still, when you have the architecture, that is kind of abstract still. So you need to specialize and you need to integrate the assets to better match the interacting components in your architecture. But still, the fact that you can do this early, because that's when we talk about architecture, and you can identify usable chunks here. Well, that means that you can identify potential reuse early, you can find candidates to reuse early, and you can start to reason about specialization and integration early. And that's a great benefit. So I will say that this is the way most programmers work. Maybe you don't talk about architecture and asset specifications, but you have it like unintentionally when you look for something to reuse. And that something to reuse can be anything from a single snippet of code to a database management system or a web server, something alike. If you look at the software product line, it is something that combines development for reuse and development with reuse. Okay, so why is this then successful? Well, what they do is that they define a product line. We will develop products in a range, similar products. So it will not be diverse products as embedded software for a car and an app for, well, a game, say. That's not a product line. A product line is what you find when you go into a consumer electronics shop and they have a range of products, cell phones, kitchen appliances, etc. That's where you find your potential product lines, because if they have software inside, well, the software is, well, it's quite likely that the software is similar for these different products. If you develop products for a specific domain, say that you have specialized in systems supporting payrolls and payroll management, well, you can have a range of 100 customers or thousands of customers, and they still are interested in a system that manages their payrolls. It's quite likely that there will be common things for all these payroll systems. There is a payroll, there is a batch processing, there are some calculations. There will also be things that vary from one product to the other. Customer-specific things, national rules, taxation, insurances, etc. But still, I don't think I need to argue too much to convince you that if you have 100 payroll customers, there will be elements in these 100 products that are common. And there will be elements of these products that are customer specific. So when it comes to product lines, software product lines, there is a systematic approach to engineer for a domain, that is the whole range of products, where you define a family of products with this commonality and with the variability. Then you can use the assets you have in the domain when you develop with reuse. You can reuse from that domain and you can specialize for a particular system or a particular customer. Okay, so when it comes to domain engineering, the problem here is always the challenge breadth versus depth. Okay, so what do I mean by that? Well, the fact that if you want to support all domains, this is like spanning the range from Candy Crush to nuclear power plant control software. And you want to provide assets with abstractions for everything, well, the problem is that you have to cover all the details for all the domains. And if you know someone who's able to do that, please let me know, because I want to hire that guy. But this is, of course, not feasible. And actually not something that we are striving for either. So, what do we do? What do we do? Well, typically, as an organization, a software house, we will look for some kind of vertical. We are experts in this vertical, this application domain. Our company are specializing in payroll systems, or our company are specializing in control software for cranes, or games, or yes, a vertical. So within that vertical, we can develop assets that are reusable. That's one take on things. Or we can go the other way. We can go horizontal here and try to cover as many domains as possible. We can specialize in communication platforms, or we can specialize in databases. That is something that is reusable across domains typically. But the biggest of all challenges here, if we want to systematically develop for reuse and develop with reuse, is to manage variability. Variability is a great challenge, and every time you talk to industry today, they mention variability. Because customers today, they expect a lot from their producers. They expect that it should be tailored for their specific purpose. Something that is okay is not good enough. It should be specialized, and even worse, it should be delivered quickly, because the markets are changing rapidly. So, from a software company perspective, managing variability is one of the biggest challenges today. There are some interesting aspects when it comes to horizontal and vertical platforms, and that is that you may actually identify these at various levels of abstraction. We can think about a games domain. At some level, that can actually be a vertical domain. But it could also be, within the games domain, a horizontal platform. Because you could find something that is spanning or useful in many games, many different types of games. So what's important here when you work with reuse is that you scope your platform, or you scope your product line platform, so that you can control the variability within this little red box here. That is your scope. That's where you develop your software. Because what's important here is that you need to harness, you need to get control of the software variability. Because if you can't control this, it will be very difficult for you to come up with a classification of the right abstractions. The only way to do that was to understand how these assets should be reused. And if you have this little small red area, well, it's much easier to understand how the assets will be reused within that little small area compared to the big blue that was shown on the first slide there. What you know is that usage will vary from one product to another and from one domain to another. But if you want to harness the variability, you must understand What? What can vary? We have a range of products. What can vary within this range? How can it vary? Are all possible combinations? You know, if you have variations, you will have combinations. Can all variants be combined into something that is complete? Probably not. So you need some kind of restrictions on what's a correct configuration. Another interesting thing is, when may they vary? You know, some systems today, they have plugins. You can download and you can install them dynamically. Some plugins require that you restart the application. Back in the days, typically you had to recompile to get a plugin into the system. So this is an example of when can you introduce a variant? When can the system change, vary? And this is all part of scoping the family. So what can vary within the family and still be a product in that product family? How? When may it vary? So it's very important that you make these decisions, because those decisions define the little red box you saw. Just to illustrate scope and the fact that it may evolve. The fact that here you have the McDonald's menu on the left-hand side during the first years, and then you have a much more recent one. So why are burgers a good examples of variability? Well, you have a bun, you have a patty, you have the cheese, you have the lettuce, you have the tomato, you have the onions, you have the sauce. Well, what you see today is that they take a regular burger and then they just like shift the lettuce and put it on top, throw in a new patty, change the cheese, and suddenly you have a new configuration, you have a new burger, a new product. So in the beginning, they had a burger and a burger with cheese, two products. Go to any of these fast food restaurants today, you will see that they have a product range which is actually a configuration of rather few base components in various configurations. You can see the same for software systems. Here's another example of a product range. Here's a very famous one, cars. What is a car today? Well, a car is a product line. What happens when you would like to order a new car? Well, you actually configure. So you go into the system and you select this model, this engine, this color, this audio system, this navigation system, this pick and choose, configure. And at the end of the day, when you push order, you actually send out a recipe. You send out a recipe to the car manufacturer, and they manufacture, they produce a product which is tailored for your specific needs and wallet. So if you look at software product lines, this is nothing new. This is actually initially first discussed back in 1960s. There was a guy called Doug McIlroy who talked about software factories, really using the analogy with integrated circuits. So, you know, you have a motherboard and then you just plug in different circuits and connect them to get some behavior. He was looking at the same, but from a software perspective. Then Dave Parnas, he introduced in the mid-70s program families, stating that we don't develop new systems, we develop variations of existing systems. And that's a very strong statement, because it means that we always develop with reuse. There's always some system that we reuse from. What can we reuse then? Is it just software? No, of course not. There is all these assets that are involved in a development project. Requirements? Sure. We can reuse statements, we can reuse scenarios, we can reuse lots of things. The architecture, detailed designs, they are also reusable. Then of course the code components or binary components, but also tests. We can reuse, if we have a system where we systematically reuse from a domain, well, in that domain you can find unit tests, you can find some integration tests, so you can actually configure your test suite based on reusable assets. Why do we do this then? Of course, we achieve these goals: time to market, improving quality, increased productivity, and we support mass customization. And this is something that customers today are really pushing for. Today, software is such an integral part of our daily life. Well, my kids, for instance, it's their life. It is their life. So if it's not customizable to a degree where it fits you as an individual, because it becomes a part of your identity almost. So if we look at the definition, when you have sets of software-intensive systems that share a common managed set, now we introduce something that is interesting, a feature. Feature is some kind of behavior that satisfies the specific needs of a particular market segment or mission. This is like horizontal, vertical discussion that we develop from a common set of core assets. It's not just a product line, it's actually a software product line. And there are lots of examples. Here are some examples, and I would just like to show you the impact of software reuse. Look at the Volkswagen engine control system, developed by Bosch, Robert Bosch. You recognize the 4 makes down there? They share the same software. You remember what happened a couple of years back when it was discovered that, there was a little configuration flag where the engine control system recognized situations where they were running the engines in test beds, test benches, or where they actually measured emissions. So they reconfigured the software. That was, of course, a fraud because the emissions were lower than the actual emissions when you drove the cars. And this was something that, since they reused, something that affected not just one make, but all makes that shared the same software product line. So if we look at this from a process model perspective, you see that, well, we have the domain engineering. That's when we engineer for the red box, for the domain we're addressing, for the common assets that are shared among the products in our range. But then we have all these products, and products are unique. One product is always different from another, otherwise it's the same product. So this little unique element are the customer-specific needs. The ones you find here. Okay? So what happens is that you have the customer needs, you perform an analysis based where you compare the domain, what you have, what you can reuse, with what you need. There are some new requirements that require some custom design, but there are some features that you can reuse off the shelf. You combine the two into a design, and you can configure a product that you can test. And you see here that you reuse requirements, you reuse designs, implementations, tests from the domain here throughout the process. So each product has its own application engineering instantiation. Then you have a feedback. It's not shown here really, but the new requirements here are considered for inclusion, because it can be that some customer comes up with the smartest feature. We'd like to have this, and you suddenly see, okay, this is something that most of our other products should also have. So you include that, and then suddenly it can be pushed out to all products in the range. So one of the core items here is the feature. And a feature is like a behavioral abstraction. So what is a feature? Well, let's turn to a system that all of you know, your cell phone. The fact that you can call, that's a feature. The fact that you can receive a call, that's another feature. There are some base features represented by base apps in your system, like a calendar. And in that calendar, there are months, and there are days, and there are hours, and you can book or make reservations there, for instance, and that's a feature. So some higher level functionality and a quality or quality attached to it. So this means that we can actually define systems not by individual scenarios or requirements. We can group them into a feature. And those abstractions are a little bit more easy to work with. And the reason we don't need the requirement level as much when we work with the domain engineering is the fact that, well, systems or our products, they share features, not the detailed requirements. So some features are common. Some features can be mandatory. They must be in all products. And some features are variable. They can be included in the product. And the combined common and variable features, that they define the scope of your software product line. Just to illustrate this quickly, think about a board game product family. What could vary here? And how should it vary? Well, if you look at, you have a tic-tac-toe and you have I think it's a checkers game there. Well, what's common here is that there is some kind of board. If there is no board, it's not a board game. Okay. Then we have some markers or chips or whatever, And they can be simple or they can be complex, because we can imagine a chess game here also as a board game. But you can see that when it comes to the board, the geometry can vary. It can be fixed geometry, or it can be a dynamic geometry. You can imagine a tic-tac-toe game where that grows until someone eventually is able to put 3 markers or 5 markers in a row. Whereas for the checkers and chess game, it's like an 8 by 8 dimension. What else can vary? The game rules. Yeah. The movement of the markers. Sure. Okay, but now we have to stop for a moment and start thinking about how can this vary? Well, we can probably not combine chess markers and chess rules with a dynamic geometry as for the tic-tac-toe game. So this is an example of constraint, a configuration constraint. This is something that we have to work with, define during the domain analysis here. What is the domain we're working with? What are the features and how can these features be combined? In order to express this, believe it or not, but we're computer scientists, we have a special model here. We have something called feature diagrams. And the feature diagram is a tree, and this tree, it has some specific nodes representing mandatory, representing alternative, representing optional features. There can be variants of a feature. A variant is providing the same or similar functionality, higher level functionality, so you can actually have different variants. Think about a car, just to make it easy. Think about a car. You have the engine. When you configure your car, you can select from a range of engines. They're all engines, but there are different variants. Same for software. So if we look at our board game example here and try to build up a feature model, we said that, well, if it doesn't have a board, it's not a board game. So a board game requires a board with some geometry. What else do we need? Well, we need some game rules, that are fixed rules. It could include the geometry, could include the markers, the value, etc. Then the dynamics, how these can be used or how they can move, etc. And then just to show you, we can have an optional user management down here. So what we can say here is that we have 3 mandatory features that must be included in all products. We cannot have a board game without a board, without game rules, and without dynamics. But we can have a board game without user management, because that's an optional feature. It may be present or not. So, okay, let's go to the dynamics. What do you mean by that? Well, that is an example of alternatives where you have variants. You can have, in this example, alternatives where you can choose between a dumb or a smart bot, a computer player. Or you can have a 2-player network, which is an optional one. But what you have to do if you have a 2-player network is probably some user management. So there might be a constraint here that restricts a 2-player network with user management. So for this feature model, we can come up with variants of the boards, variants of the game rules, as you see, variants for the dynamics and how they are managed, if it's like a user dynamic part E, or if it's computerized parties involved in the gameplay. And this feature diagram identifies what could vary. With constraints, we can constrain how it varies. So this is a model that exhaustively scopes our product range. Our next step is to implement variability, because we have a product range, we have features, and now we would like an architecture that is common to these products. And in this architecture, we need to install mechanisms that makes it easy for us to include alternative and optional features. That supports the inclusion of a feature plugin at runtime, or at load time, or at compile time. So we'll look more at that, and I think it's time for a break, a little bit early, but it's better to take a break now, and then we come back after the break and we focus on the architecture design. Okay, but let's take 10 minutes. So, okay. I think we're back. Checking here. Yes. So we were dealing with this board game product family. And we define a feature model. Simple one, stupid one, sure, but it's a feature model. Next step now is to design for the domain. And what we have to consider now is actually a couple of important things. We need an architecture. And this architecture is a reference architecture, which means that it should actually be able to host all products with the commonality and with the variability. So what you do is that you actually design an architecture with explicit variation points where things can vary. And this can be in different points, in different views. It can be in a requirements view, it can be in a design view, it can be varying in time so that you can vary it at runtime, but you can also vary it at load time or design time or, yeah. What do you mean by vary? Well, a variation point means an open decision. Remember the architectural decision points? You make decisions. And a variation point is actually a decision we haven't made. So you make these decisions, and you can make these decisions at various points in time during the software lifecycle. So if you have a runtime decision, it means most often that the end user can configure something at runtime. Flip this on, flip this off. Install this feature, uninstall this feature. And what's important now is, of course, that, well, you have an architecture and a variation point, but this variation point is just in the architecture. Now it has to be represented in the code. It has to be mapped, for instance, a runtime variability mechanism is a piece of code. If we talk about plugins, well, most of you are familiar to some integrated development environment like Eclipse. Eclipse can be a very, very, very small thing, or it can grow using plugins. Something that is more or less a beast. But it's supported by variability mechanisms. It's the same core application. So if you look at the software product line, it's a product line architecture here that can be instantiated to products by configuring it with different components. And some components are external and others are internal. What do you mean by that? Well, remember the domain. If it's in the domain, it's internal, but you could, of course, always add components that are external, not in the domain. Okay. So designing an architecture platform, people use these two words interchangeable when it comes to software product line. The effective design is really the difference between success or failure. We talked about determining the scope, but then you need this abstract, this reference architecture, this platform design that includes the variation points represented by mechanisms, runtime, or variability mechanisms, different design principles. You need a class hierarchy typically for the variants of your components. You need design principles so that people can design their own plugins or components to extend. It's a huge undertaking. It takes a lot of time. It's a huge investment. Huge investment, that means money. That means time. And there are many investigations into when does this product line approach become, so to say, not a red number on the final row, but a black number, when it's profit from this approach. And on average, it's 4 products. When you have 4 products developed, you have amortized all the investments you made into your platform, into your product lines, sorry. So, in your domain design and domain implementation, you design for variability and you implement the variability mechanisms. So a simple example, a very simple example. Picture manipulation. You have a picture coming in from the left, exiting on the right. And in the middle you have kaleidoscope, which is your application that manipulates the picture into something picture prime. Okay. This is the principal architecture. What you need to do now is, of course, to start figuring out, well, what type of features you should have in the system. You should come up with some kind of design. And what you can say here is that you should be able to manipulate pictures in different ways. Otherwise, this will be kind of a useless application. So you should be able to configure your kaleidoscope applications to meet the customer-specific needs. They will have some common features, and they will have some variable features, some customer-specific features. So if you choose to implement your platform as a framework, well, I would say that why not go for a pipe filter architecture here? Remember the pipe filter architecture pattern? That was when you had data streaming into a filter, exiting on the other side somewhat manipulated. So what you can do here is that you can, we have in our reference architecture, in our product line platform here, we have something, an abstraction that we call picture, and an abstraction that we call filter. We need a pipe to connect filters, but with these we can actually build something that manipulates pictures using a sequence of filters. So this is the principal reference architecture. Now we come to the other side, and that's actually the variability. So what is variability here? Yeah, what is it? Support for different picture formats. Sure. If we only support JPEGs, not very popular. Potential market segment is small. If we support more picture formats, more popular, more customers, more money, more, yeah. Different types of filters. Sure, why not? Because remember the mass customization? Mass customization meant that we had customers with very specific needs. And if we don't meet their specific needs, they are not our customers. So we need loads of filters, doing compression, doing stuff like comic balloons, like Homer here. We need to apply a combination of filters, like configuring the filters in different sequences. We might allow for variability where users define their own filters. and their own picture formats. Well, the sky is the limit. Your ability to support this is actually the limit. You can sit for days just thinking up what you can vary in an application like this. The problem is the scope. And the challenge is to come up with an architecture where you actually define the design principles so that people can do this, so that people can define their own filters, plug them in, configure them together with other filters, and it works seamlessly. Or someone defines their own picture format. What will be the consequence if you define your own picture format? Well, you have loads of JPEG filters, you have loads of GIF filters, and et cetera, et cetera. But if you define your own picture format, what will happen? Will the old filters work, or do you need to specify not just your own picture format, but also your own filters? Or is there something in between? Can we define an intermediate format that we have just one filter type that performs the manipulations, and then we have an export at the end. So we export back to the original format. So we read in JPEGs to this internal format, we manipulate them, and we export them back to JPEG. That's another approach. Maybe that's more flexible. Those are the type of decisions you have to make. And you need to come up with an architecture design that supports this, what I would say, flexibility, variability at different points in time. Just to illustrate what I mean by the mechanisms and the principles. Here's this is an old example, but it's still valid because it's graphical user interfaces, and most of you are familiar with some kind of graphical user interface library, and most of them are organized somewhat like this. So the Java AWT and the Java Swing library on top of that, and the Java FX on top of, well, that, they are kind of similar here. But if you look at the Java AWT, which is the AWT, which is the basic one, it has a principle that defines the architecture of all graphical user interfaces that uses this library. And the fact that you have a container, which is a component, and this container consists one or more components, means that you can actually create a hierarchy of containers that include components. So you can define your menu with menu items. You can define your windows with various controls, with various widgets. And they are all laid out using layout managers. And there are different types of layout managers, different types of algorithms. Some are dynamic, considering the geometry of the screen. Others are fixed. Okay, so now we can create, instantiate different variants of our containers, different variants like panels, windows, scroll panes, frames, dialogues, and then, well, you know, all the things, buttons, text fields, etc. below. We can create a static UI. However, a static UI is not very fun, so we need some dynamics. And parallel to this static structure, the AWT has a message system with events and handlers. So these components here emits events depending upon what happens. And then you can have handlers that takes care of these events. So this is an example of a structure and a mechanism that is part of this reference architecture for Java AWT user interfaces. There are loads of, well, variability mechanisms in here. The fact that you have a container and you add components to that container, you add with a method, that's a variability mechanism. You can quite easily during well, the coding phase, compilation phase, vary the user interface. You can even do it dynamically. You can create your interface dynamically by instantiating a component and add it to a container. Okay. So now say that, well, we have this pipe filter, we have some kind of communication, we have decided on the internal formats for pictures, what the filter looks like, what's the interface for receiving pictures for a filter, what's the interface for sending out a modified picture for a filter. You need to design on the mechanisms. How do you compose, how do you combine filters into a chain of filters or whatever it is that manipulates the pictures. When you have that, well, you can start to evolve the design, adding support for variability. User-defined filters, what is that? User-defined picture formats, what is that? How do you add do you have a specific variant supporting, well, comic balloons with text on your pictures? And then, of course, you need continuously to maintain, well, the patterns, the design principles, because you will have a domain up here, and then you will have application engineering projects down here. And there must be some guidelines. And the more guidelines you have, the more easy it will be to develop with reuse. So just to look at what is the output here. Well, you have a software product line with a product line architecture. And in your architecture, you have variation points. These are like the red ones here, are variation points. And these variation points are supported, could be supported typically if it's supported in the code, by code. It can be an inheritance hierarchy. That can be an example of a variability mechanism. It can be in a very advanced plugin behavior. But it could also be a variation point in your requirement. Select blue or black. That's a decision that you can make during requirements. Then you have your internal components, filters, picture formats, etc. And you have variants of them. You have support for JPEGs, you have support for GIFs, you have support for various manipulations. Okay. You can also have external components, not part of your software product line, but still it's possible for a customer to define their own picture formats and make them work in this picture manipulator product line. And of course, you need to define different products here. The great challenge here was actually to see if I can map all these variants, configurations, to the variation points and variability mechanisms. Maybe it's not perfect, but it's just an illustration. Okay, so if you look at an organization where you remember the payroll company, 100 systems, well, suddenly you need to scale things up. And it's not just about product domain engineering or product engineering, it's a lot about product line management. So, and this is not an uncommon role. You see this quite often actually, that the company has a product manager. And this product manager is managing all the products in a range. And they are responsible for maintaining, evolving the scope. Evolving the scope means meet new requirements. Consider, should we include this or shouldn't we? Say that you have one customer who wants a new feature, or you have 10 customers that wants a new feature. Probably more value if you decide strategically to support that than this single customer. You can take into account that, well, you can talk about value streams, what creates value for your company and your customer. Is it worth it? Should we invest time to take this new feature that was developed for your specific customer into the domain? Yes or no? This is a very powerful mechanism in your development organization. So, finishing up, software design for and with reuse. We need architecture as a support, because I can't think of anything more architectural than deciding, for instance, on what type of persistency storage should we have. Well, most often you reuse that. You don't develop something from scratch. If there is a component in your architecture with some responsibilities that you can reuse, and you can do it quite easily without too much specialization, well, why shouldn't you? The problem, the challenge here is actually when you develop for reuse to predict how will this be reused. And when you reuse, to specialize, to make it work within your product. So software product lines is trying to, by narrowing down the scope, addressing this problem of prediction. Because within a restricted domain, like a product range, it will be easier to predict. It will be easier to come up with good abstractions and to classify them in a way that they are easy to find. So restricted domain, identify what's common and what's not in this domain. Define your products using features. Come up with a product line architecture that supports the variation and provides a backbone with the common features. And there are many studies that shows that if you do this, if you succeed with it, you can boost reuse levels up to 80% and more. There are examples way up above 90, 95%. And speaking of market competition, if you have an approach where you can reuse 95% of your application compared to your competitors, well, your offers will be the best, and you can still have a larger margin in your business. Okay, so that's all, folks, for today, actually. I will put up the new assignment tomorrow. I started to grade, or I started to download and read your submissions for the second assignment. Next week, there will be some guests talking about, hopefully, cloud architecture for different deployments, and also service-oriented and microservices architecture. I'll be traveling next week, so I will not be here. I will also put up some reading guidelines for you guys to prepare for the home exam that is up in a couple of weeks. But until then, don't hesitate to post questions on Slack. Okay, so I see you then. Goodbye.